Hey, what's up? It's your old pal, Mr. Cook, and we are working through these problems from the Unit 4 test review. I already made a video going over um, a way to identify which method to use. So I'm going through each. So I'd recommend watching that video first, and then now I'm working through each method. So in this video, we'll do the partial fraction decomposition. So it looks like partial fraction shows up just a couple times in this worksheet. It's a pretty easy technique. Excuse me. Sometimes it's not like super easy to spot. Basically, like if you have a quadratic in the denominator, or a polynomial, I guess in general, and you can factor it, then you can use partial fractions. The idea comes from when you add fractions. So if you have like two fractions and you're adding them together, you got to find a common denominator first. So like an easy way to do that is to take one's denominator and multiply it in the numerator and denominator of the other fraction, and do the same thing for the other one. So just like, take the other one's denominator basically and multiply it over. All you guys probably learned this, back in grade school, and that technique helps out a lot. So, for the first fraction, you get 3 over 12. For the other one, you get 4 over 12. And then you combine them together, right? 3 plus 4 over 12. That'd be 7 over 12. Well, imagine that you've got some quadratic and you've already got it factored to where you've got, you can split a fraction apart, right, into the sum of two different fractions. Because basically you're looking at this as a least common multiple of two factors of an expression. Okay, so that is the common denominator, if you will, for the sum of two fractions. So what this method allows you to do is to split this product into sums of a fraction. Okay, so here's what our goal is with partial fractions. We start off with some polynomial, and we should be able to factor it, like what we've got over here. And then what we do is we split it apart into two separate fractions with some numerator, we don't know what it is, over the x minus 4 part, and then plus some other numerator over the other denominator part, the other factor in the denominator, x plus 5. So basically what we do is we reverse engineer it. We start here, and we got to find our way back over to this original expression. And here's how you can do it using this partial fraction decomposition. So the idea is this, so think about how you would go from here to here. Okay, so this is kind of like our goal on this side. Okay, we got to figure out what A and B is. Well, if you were to combine the fractions together, you'd have to find the common denominator. So this is what you'd have to do. And you don't have to do these steps every single time. I'm going to show you a shortcut in a second, but basically the idea is that you would take this denominator and multiply it in the numerator and denominator of the other fraction, just like what you did with 1/4 and 1/3. And then you'd multiply this denominator and the other fraction. So you'd have b over x plus 5 times x minus 4 over x minus 4. Okay, because if you do that, then you have this common denominator now, right? And you can combine the fractions together into one. So it looks something like this: a times x plus 5 plus b times x minus 4 over, the common denominator, which is x minus 4x plus 5. And now do you see why this helps out? It's because the thing that we just created here, this fraction over here, is the same as this fraction. So the denominators are the same, so that means the numerators must be the same. So 1 is equal to all this stuff up top. And that's how you can actually find a shortcut for this. Once you find that common denominator and those multipliers, you can just set this equation equal to 1 and then solve. Now, when you get into differential equations and multivariable calculus, and you might have to do this, and it might be a more complicated denominator, it might be helpful for you to learn how to write this up as a system of equations. So I'm going to show you that, but usually I just use a shortcut for this part as well. But I'm going to show you the system of equations first, okay? So if you distribute the a in there, ax plus 5a and you distribute the b in there, bx minus 4b, that's equal to 1. And then if you were to combine like terms, the x values would combine. So a plus b times x. And then combine the constants together and you would get, 5a minus 4b, right? So notice that there's no x value over here on this side, right? So it's like adding a 0x. So it's saying that this part has to be equal to 0 and this part has to be equal to 1. Like that's your system of equations. A plus b equals 0. And then 5a minus 4b is equal to 1. And then you can solve for a and b using that. I don't like to use that on these easy ones because there's a really easy way to do it. And so it basically says this, like, this equation is supposed to be true for mostly all x, okay? And so if you strategically pick some x values, even though they're not allowed to be used in this rational expression, but we'll ignore that for now, you can actually solve for the a and the b values. And here's how you do it. If you want to solve for a and b from this one equation, a really easy way to do that would be to set x equal to -5. Because if you let x equal -5, then it becomes a times -5 plus 5, which would be 0, cancels out the a, and then b times -5 minus 4. And that's a number, right? So this part goes away because it's 0, and then you have a -9b equals 1. So that means that your b value is equal to -1/9. And you would have found that from the system of equations as well, but this is just an easier way to do it. So I'm going to write -1/9 up here. And, similarly, you can strategically pick another x value to cancel out the b. If you plug in 4, it'll work out. So I would get a times 4 plus 5 plus b times 4 minus 4 equals 1. So that means that 9a is equal to 1. That means that a is equal to 1/9. So you can replace that a up there with a 1/9. So like you need to solve for the numerators in these cases, but it's pretty easy, pretty straightforward for the most part. Okay, so once we have those numerators though, this becomes a really, really easy u substitution. And if you need some practice with u subs, you can go ahead and watch the video on u subs that I made. But I'll do one u sub here and then I'll show you that it's pretty easy. Like in this one, the first one, we have that 1/9 there, but the x minus 4 is what I'm going to set equal to u, and du is going to be equal to dx. So this top part just becomes like 1/9 integral, or this first one, 1/9 the integral of 1 over u du. And that one is going to turn into 1/9 natural log absolute value of u, which is x minus 4. So that's like the first one. And then this other integral is going to be, let's see, if I let u be equal to x plus 5, du is equal to dx. So that means that the other integral I get is a -1/9, 1 over u du again. And so for that one, I get -1/9, and then natural log absolute value of u, which is x plus 5, and then plus my constant c. So there you go. That's the first partial fractions problem. All done with that. Okay, let's see. I think there's one more partial fractions problem here. Yeah, I think it's just that one, 31, right? Yep, so just those two. So this will be a relatively short video. Okay, now this doesn't look like partial fractions, but notice that we have a quadratic in the denominator. If we just factor it, then it'll be more apparent that this is partial fractions. So there are numbers that multiply together to be -14 and add together to be -5. That's going to be -7 and +2. So this becomes x minus 7, x plus 2. And then if we just go through our partial fractions algorithm, this would become, let's see here, 1 over x plus, or a over 1 plus x plus 7, minus 7, sorry, plus b over x plus 2. And then, when I multiply by the denominators, right, I get a times x plus 2 plus b times x minus 7. And that's going to be equal to just this numerator over here, 1. Now, if it was a 3 over here, I'd set it equal to 3. It just so happens that this one's equal to 1. So, just put a 1 there. And then if I pick x is equal to -2, then I get the a cancels out. So I just get b times -9 equals 1. And that means that b is going to be equal to -1/9 again. Okay. That's not always going to happen, by the way. It's just, this case it does. And then the other x value that I should use is probably 7. And if I do that, then I get a times 9 equals 1. And that means that a is going to be equal to 1/9. It's just that like our terms that we have, like, the factors, -7 and +2. And then the other one we had 4 and 5. So those make 9s naturally. Okay, anyways, then we would do a simple u sub on these ones, and we'd end up with the following: 1/9 natural log absolute value of x minus 7, and then minus 1/9 natural log absolute value of x plus 2. And that'd be it for this one. Okay, and that's also it for this video. Only 2 problems with partial fractions on this worksheet. So there you go. That's it. If you need some more help with partial fractions, reach out to your calc teacher. Hope this video helped, and I'll see you in the next one. Bye-bye.